so now I want to draw a picture. So this is alpha. This is beta. And alpha and beta are orthogonal because alpha does not include the basis state beta in its sum. And here is psi equals, what was it? 1 over root n beta plus remaining alpha, root n minus 1 over root n alpha plus 1 over root n beta. And we're assuming n is large, so this is very close to alpha. The overlap, the inner product of alpha and this is root n minus 1 over root n. And now we want to look at 2 psi minus I. So what does this unitary transformation, well, you can see it's unitary right here, do? It does nothing to psi. Right, so I don't know what to call this. So we could just call it by 2 psi minus I applied to psi is just 2 times psi minus psi equals psi. So what I want to claim is it takes a state here and it reflects it around the line psi. So, assuming it's a superposition of beta and alpha. So we just have to worry about states that look like alpha plus beta. So x alpha plus y beta. So I see that I did not prepare this well enough because I thought it was obvious when I was preparing, and there probably is an obvious explanation for it, but I don't see it right now. So 2 psi minus alpha minus I applied to alpha is equal to 2 psi alpha minus alpha okay. Well, 2 psi times alpha is going to be some product of psi. It's going to be some multiple of psi, and alpha is going to stay the same. So it's and psi was what? Psi was 1 over root. So let's take this. You get psi is equal to oh no. Yeah, psi equals root n minus 1 over root n alpha plus 1 over root n beta. So you take this inner product, you get 2 root n minus 1 over root n alpha plus 2 rather 2 root n minus 1 over root n psi plus minus 2 alpha is equal to root n minus 1 over root n alpha minus, okay, I don't think this is the right way to do it, plus 1 over root n minus 1 over root n beta minus 2 alpha. So we started with alpha. So we started with alpha, and we ended up with 2 root n minus 1 over root n beta, which I think you can so we start with alpha, we end up above this, and it's a unitary transformation, which means angles are preserved, inner products are preserved. So after the unitary transformation, this angle has to be the same as that angle. And we started out, no, we clearly end up above this line. And we started out below this line, and inner products have to be preserved, so this has to go to that. And it also is a unitary transformation, which means it's, it preserves the plane. So if this point gets reflected up to here, the entire plane has to be reflected around this line. So this is what it does in. So this reflects a line, reflects this alpha beta plane around the line psi equals root n minus 1 over root n alpha plus 1 over root n beta. So what does the other thing do? The other thing is x goes to, is the oracle x goes to minus 1 delta beta x. Well, what does that do? It does nothing to alpha, and it reflects beta around the line x equals 0. Around, I guess, the line alpha equals 0. Which is, I guess, y equals 0. So what this Grover algorithm, what this Grover iteration does is it first, takes this point and reflects it down here. And let's say this angle is theta over 2. And it then takes the point down here and reflects it not around the y-axis, but around this line psi, which is just a little bit above the, about just a little bit above the x-axis. And so what happens when you take one reflection and then another reflection in a slightly, slightly skewed line? Does anybody know? Yeah?
Looks like a rotation.
It's a rotation. And it's a rotation of angle theta. And how can you see that? Well, I mean, you can break this. Okay, I really should do it for something more general than this thing. So, I mean, suppose we started here. This going down would be let's call this angle gamma. Going down, we would have to reflect it around here, so the angle below here would be theta over 2 plus gamma. Gamma. And then reflecting, then reflecting around this. Well, we have this has an angle of theta plus gamma with respect to this line. So above here, it would have to be theta plus gamma. So we started at an angle of gamma, and we ended up at an angle of theta plus gamma. So that means we take whatever thing is and we rotate it by an angle of theta. Okay, now we're basically done all the hard work for Grover's algorithm. Let's see, what do I want to erase? This. So we have sine of beta over 2 is equal to 1 over root n, just because this is 1 over root n times beta plus root n minus 1 over alpha. Now we're going to assume n is big. That means theta over 2 is approximately 1 over root n. And we want to ask how many iterations to get to. To get to pi over 2. Because we want to take as many iterations as we need to get to something very close to this angle beta, this vector beta. And then when we measure it with high probability, we get the answer. Well, it's pi over 2 divided by, well, each of these angles is 2 over root n. 2 over root n is equal to pi over 4 times root n. So after pi over 4 times root n of these iterations, we have a quantum state that is very close to beta. And when we measure it, we probably get our marked state. Yeah?
Can you explain again what beta over 2 means?
Theta over 2 is this angle. The angle between, so we're alternately reflecting it around the x-axis and this line psi. And it's the angle between the x-axis and the line psi.
So what are we reflecting? We're reflecting the line psi?
We start with a quantum state, which is, have a quantum state. state, which is A sub alpha alpha plus A sub beta beta. So that is somewhere on the unit circle here. And we start by reflecting it around the x-axis, and that corresponds to this thing. And so we go down here. And then the next step, reflect it around these three things reflect around psi. And that takes it and moves it up there. So that's one Grover step. And it changes the angle by theta. And we want to ask, how many times do we need to change the angle by theta to get to the state beta, which has an angle of pi over 2? And the answer is pi over 2 divided by theta, which is roughly pi over 2 divided by 2 root n, which is pi over 4 times square root of n. So that's Grover's algorithm when there's one thing we're looking for.